Welcome to the 29th lecture in our particle characterization course. In the past couple of lectures, we have been looking at methods of characterizing the chemical and compositional properties of particles. And initially, we started by discussing microscope based methods, then we looked at techniques for organic materials. And then in the last class, we discussed two techniques in a little more detail: atomic force microscopy and X-ray diffraction analysis. And I mentioned that the, the importance of the analysis technique becomes increasingly evident as particle sizes decrease. And when we get into the nano size range, it becomes extremely critical that we use the most appropriate method to analyze these particles. Now, before we start discussing methods of characterizing nanoparticles, I want to take a few minutes to talk about some basics of nanotechnology. Including methods of synthesizing nanoparticles, methods of dispersing them in suspensions, and finally characterization of the various properties of nanoparticles and nano suspensions. Now, the reason that it is important for us to spend some time discussing the basics of nanotechnology is that nano is like the proverbial elephant and the blind man. It depends on what aspect of nanotechnology you deal with, you have a very different perception of what nanotechnology is. So, it is very important to have a more common understanding of what constitutes nanotechnology. So, the outline of this module is going to be as follows. We will begin by defining some terms. What is nanoscale? What is nanoscience? What is nanotechnology? We will talk about some applications of nanotechnology, methods of synthesizing nanoparticles from the bottom up approach and the top down approach, and finally characterization of nanoparticles, which we classify as qualitative methods and quantitative methods. So, what is nano? You all have seen the car that is made by Tata. Is the nano, does it fit the term? Is it really nanotechnology? It is small, but is that sufficient to qualify it as nano? The way we perceive nano, nano gives a connotation of something that is technologically very advanced, something that is state of the art. Is nano representing that? I think so. I think the nano car, when it was introduced, did represent a huge breakthrough in manufacturing technology, if nothing else. So, I think it does fit the label of nano very well. But what is nano? It is a dimension. It is nothing more and nothing less. Nano is a linear dimension. It is actually derived from the Greek word for dwarf. So, clearly the connotation of small size is there, and it is 1/1000th of a meter or 10 to the power minus 9 meters. Now, just to give a perspective of what that is, if you look at various objects that we encounter in life and look at their dimensions, a common insect like a flea is roughly 10 to the power minus 3 meters in length. The human hair 10 to the power minus 4 meters, blood cells 10 to the power minus 5, bacteria 10 to the power minus 6, viruses are 10 to the power minus 7, DNA is 10 to the power minus 8, molecular structures are 10 to the power minus 9, and so on. So, if you look at this nanoscale, the last three, that is starting from roughly 10 to the power minus 7 to 10 to the power minus 10 is what we would refer to as the nanoscale. Now, there are three key nano terms: nanoscale, nanoscience, and nanotechnology. Let us take a few minutes to understand what these are. When we say nanoscale, do we mean that all dimensions of the object have to be in the nano range? No, not really. As long as one of the dimensions sits in the nanoscale, we can consider it to be a nano object. Is 1 micron considered nanoscale? Conventionally, no. But is 999 nanometers considered nanoscale? According to convention, yes. So, it is not a very clear definition. I mean, why would you call 999 nanometers as nanoscale and then 1 nanometer more as micron scale? It just traditionally that is how particle sizes have been referred to. And again, is human hair nanoscale? No, because it is actually very, very long compared to the nano dimensions. So, what is nanoscience? Any new discovery goes through two stages. One, first you develop the science of it, then you develop its technology. Now, the difference between the two is science is something that you do in a lab. It's something that you do in a small scale to really understand the fundamental physical and chemical properties of the system or material. Technology is essentially scale up. You take something that you have developed in a laboratory and you scale it up first to a prototype scale, then to actual production scale. So, technology is essentially translation of science into practice, but it starts with the science. Until you develop the science, you cannot develop the technology. So, nanoscience is defined as the study of unique physical and chemical characteristics exhibited by particles in the 1 to 999 nanometer range. Although again by tradition, nano is mostly used in reference to the 1 to 100 nanometer range. Strictly speaking, it ranges all the way from 1 to 999 nanometers, but in practice people use 1 to 100 nanometers as a nano range. And you can see some examples of nano materials here: silver, gold, spheres and prisms and so on. You can see that there are some distinct size and shape characteristics associated with nanoparticles as well as color. So, these are some of the unique properties of nanoparticles that we try to exploit in nanotechnology. Some of the differentiable properties that you can observe at nanoscale, differentiable in the sense that these properties are very different at nanoscale compared to the micron scale, and these are optical, electrical, magnetic, catalytic, phase change properties, electrochemical properties, etc. So, we will talk about some of these unique nano properties later in this module. So, what is nanotechnology? It is the application of nanoscale materials and nanoscience principles at sufficiently large scale to impact society. In other words, you do not let nano just be something that people play with in their laboratory. You try to make useful products with it that actually have a commercial value to the consumer at large, and that is what is known as nanotechnology. So, leveraging the unique properties that surfaces display at nano dimensions, characterizing the unique properties is nanoscience. Leveraging or making use of such properties is nanotechnology. It is to learn how to harness nanotechnology without harming the environment. There are many concerns about use of nanoscale materials, including their possible ecological, environmental, even human health aspects. So, technology, when you start using nano in large scale, you really have to start worrying about these possible consequences. So, that is part of nanotechnology. Optimizing without compromising. As a technologist, someone who is trying to do scale up to large volumes, your focus should always be on optimizing the process in order to get maximum throughput at highest quality with minimum energy expenditure at minimum cost and so on. But at the same time, you want to do this without compromising the functionality of the nanomaterial you are making. You do not try to cut cost by truncating the usefulness of the nanomaterial. So, that is again part of nanotechnology. Now, nanotechnology is very interdisciplinary by nature. Unlike nanoscience, if you look at nanoscience, it is still being primarily driven by physicists and chemists. However, if you take nanotechnology, the physicists and chemists are still involved, but engineers of virtually every discipline are also involved. So, it is really a confluence of various engineering and science disciplines that drive nanotechnology. What is the history of nano? Well, actually started back in 1959 when Richard Feynman stated his vision of there being plenty of room at the bottom. He said you can always keep driving technology to smaller and smaller dimensions. He basically said that microtechnology is actually a frontier that we need to keep pushing back, just like high pressure, high vacuum, low temperature, etc. So, his thinking was micro is small, but we can get smaller. So, let us keep pushing the boundary. His vision was that we could make machines that build smaller machines, that build even smaller machines all the way down to atomic level. And to a large extent that is what we have done. I mentioned yesterday in the last lecture that the atomic force microscope is one that can be used not only to characterize surfaces, but even to manipulate surfaces. It can be used to manipulate atoms. So, essentially we have built a machine that can manipulate matter even at atomic level. But there was a big gap from 1959 to 1981. Nanotechnology was really not taken up seriously as a subject of investigation. In fact, it was in 81 that the first journal publication of an article on molecular nanotechnology was published by Drexler. Now, if you look at nature, there are many examples of nanostructures. There is a human bone, silk, rat's teeth, peacock feather, spider web are all classic examples of structures that have nano dimensions at least in one scale. Now, IIT Madras has been one of the leading research institutions in nanotechnology, and Professor Pradeep in the Department of Chemistry has done a lot of work in this area. This was an interview from him in the Hindu newspaper in 2007, now defining nanotechnology. The term nanotechnology refers to a broad range of technologies, all of which involve the utilization of the properties of nanoscale objects, the unique properties of nanoscale objects. It refers to the size regime of nanometers or 10 to the power minus 9 meters. The properties of the materials in this size regime are unique. Nanotechnologies become possible as we develop capability to manipulate matter with atomic precision. At the scale of nanometer, all disciplines converge. Therefore, it is a fusion technology or interdisciplinary technology. Continuing with the same interview, why is it necessary to know about nanotechnology? Because nature is nano. Every molecular assembly in nature is basically built up by an atom by atom approach. These synthetic routes are the most energy efficient, green and sustainable. The motion of a muscle fiber or a flagellum is a result of nanotechnologies. If you look at how the human body works, it's amazing. It's all down to the nanoscale. Therefore, ultimately an understanding of these will help us do things better with improved efficiency in a more eco-friendly and sustainable manner. Also, when you look at properties at the nanoscale, there are many new things to find, to discover. So, our spirit of scientific inquiry is also kindled. Our curiosity is another thing that makes nano very attractive as an area to work in. More recently, in January 2011, there was an interview that Professor Pradeep had with the Times of India newspaper, where he said from clean water to detecting ailments, nanotechnology holds the key. In fact, more recently nanobio has emerged as a very interesting discipline to work in. The interaction of nanotechnology with biology has produced some exciting results and has been used to create new materials. This is a bio-nano interface which can help solve many problems: water, food, health, environment, etc. Hazardous and toxic impurities like arsenic can be removed from drinking water in a cheap and effective manner using nanotechnology, and many of these technologies have now been commercialized and are available in the market at very reasonable prices. Now, moving away from nano in nature, if you look at nano-engineered products, again there is a huge number of them. Virtually every manufacturing industry in the world today is impacted either directly or indirectly by nanotechnology. The semiconductor industry, where nanocrystallites are now being used in microelectronics, which should actually now be called nanoelectronics rather than microelectronics. Ceramics that are made for use in highly demanding environments in terms of temperature, corrosiveness and so on, now use nanomaterials for improved protection. Polymers are being fabricated with enhanced functional properties, primarily by making composites of them with nanomaterials. Transparent coatings with UV or IR absorption properties, abrasion resistance, all of these are now being commercially manufactured using nanomaterials. Static dissipative films, conductive films, particularly for packaging applications, use nano components. Enhanced heat transfer fluids use nano. Nano fluid technology is something that is finding increased use, and again we will cover this in more detail later in this module. Catalysis, since catalysts primarily help chemical processes by means of providing extended surface area, nano catalysts have a huge advantage over larger sized catalyst materials, and therefore nano catalysis is an area that is just taking off. Topical personal care and pharma products, and finally ultrafine polishing of memory disks, optical lenses, etc. use nano materials as the polishing medium. So, just to go through some examples of this, functional polymer fillers. Carbon nanotube is widely used as a filler material, but there are others as well. Primarily this is to improve the viscoplastic properties of these polymers. The fillers are predominantly inorganic materials like glass fiber, talc, kaolin. The dosage is 20 to 60%. However, the disadvantage is that there is an increased density of the composite materials, which can lead to higher weight, and when you have applications where the weight of the material is a limiting factor, nano composites do have a disadvantage over the pure or virgin polymer materials. One of the first uses of nano composites was the nano clay bentonite, which was used in the late 80s by Toyota for automotive applications. Functional polymers are actually very versatile. Even tiny amounts can have dramatic impact. The 20 to 60% dosage mentioned earlier is a fairly high estimate, and in fact it has been found that nano materials, nano fillers can start having an impact even at 2 to 5% by volume. Now there are many other applications. The applications of nanoparticles encompass so many different areas: industrial, electronics, environment, renewable energy, textiles, biomedical, healthcare, food, agriculture, etc. And some of the examples are cited here. Nanowires and nanotube arrays can be used for EMI shielding. Extremely high sensitivity sensors can be fabricated with nanomaterials for detecting gas leaks, humidity, and so on. Ceramic MEMS technology now uses nanomaterials. Many devices used for energy conversion employ nanotechnology, and in the electronics and related fields, nanotechnology finds wide usage as well. Other applications include anti-fouling coatings, particularly for marine environments. The nanoparticles are laid down as a layer on the surface and also incorporated into the lattice of the basic material, and they actually provide long term protection by slow release phenomena, and bacterial and antibacterial or antimicrobial coatings are possible using nanotechnologies. Textile fibers can be hugely improved by incorporation of nanomaterials. For example, nanoparticles incorporated in nylon and polypropylene provide antimicrobial properties in extreme environments even after extensive thermal cycling. Nano-sized zinc oxide and copper oxide in synthetic fibers provide additional enhancements in properties without affecting color or clarity. Permanent coatings can be laid down using nanomaterials in many applications, and again catalysts where we can use thinner layers, less usage of precious metals is possible with catalysts. Very high stability solids dispersions can be used. One of the key applications is in automotive converters, where increasingly nano catalysts are starting to be employed. Fuel cells, sunscreen products, semiconductor polishing are all other examples of where nanomaterials are used very effectively. So, given that we have this variety of applications that nanomaterials are used in, we have to start with what drives these technologies, and the starting point or the fundamental building blocks of nanotechnology are the nanoparticles. They are the starting point for preparing nanostructured materials and devices and therefore their synthesis and characterization are critical focus areas. In order to be able to control the quality as well as the quantity of nanomaterials, you first have to be able to measure them, and that is where characterization comes in. Unless you can measure the properties of these nanoparticles, you cannot optimize them for any specific application, and you cannot even control the process very well. So, synthesis and characterization go hand in hand, and so what we will do in this module is first talk about synthesis methods, and then we will switch over to talking about characterization techniques. So, what are the two basic types of synthesis methods, bottom up and top down? The difference between the two is that in the bottom up approach, essentially you take atoms or molecules and you tie them together to make nanomaterials. So, it is essentially an assembly process, very much like what is done in nature, in the sense that what you are doing is taking these atoms or molecules, causing them to interact both physically and chemically. So, by bringing these molecules together, you can take advantage of their cohesive properties to bind them together, but you can also take advantage of their enhanced reactivity to make them react in a certain fashion, so that the output that you get is regularly arranged molecules in ordered molecular orientation. So, this is the nanomaterial that you can synthesize by using the bottom up approach, and there are various methods of doing this: colloidal processes, liquid phase synthesis, gas phase synthesis, and vapor phase synthesis, and we will talk about this in more detail later on. And then you have the top down approach, where you begin with particles that are larger in size, for example micron sized particles, and you basically fragment them to produce finer particles. So, high energy ball milling and sonofragmentation are examples of top down techniques that are used to synthesize nanoparticles. Let us talk about some of the bottom up approaches first. What is a colloidal process? Well, in this process, essentially you build up the nanomaterial an atom at a time. So, you take the specifications that have been laid down for properties of the nanomaterial, and you take nanoparticles and assemble them in a certain way to be able to meet these specifications in order to be able to perform a specific task. So, this requires essentially surface active agents, surfactants, coordinating ligands to produce these clusters. So, in order to get these nanoparticles to bind together and make a nanomaterial with specified properties, you have to be able to do manipulations at atomic level. So, it is a more complex process compared to, for example, the top down approach, but the advantage is that you have very precise control over the physical structure as well as the chemical properties of the resulting nanomaterial. Some of the examples are 50 nanometer particles of cadmium sulfide that is produced by mixing two solutions containing micelles of sodium sulfosuccinate in heptane. Another example is antiferromagnetic nanoparticles of Fe2O3 that are produced by decomposing FeCO5 in a mixture of decalene and oleyl sarcosine. These are examples of nanoparticles or nanomaterials that are obtained by taking two reagents and mixing them together at molecular scale to produce a nano-dimensional material. Vapor phase synthesis, on the other hand, is one where you essentially saturate the vapor phase with the nanomaterial that you are trying to synthesize, and then you actually make it thermodynamically unstable and leading to the formation of the desired material. So, the way that you make a saturated vapor phase unstable is essentially by providing sudden cooling. In the example that is shown here, this is done by essentially inserting something called a cold finger into this mixture, which immediately results in the formation of these nano sized particles from the vapor that is present. So, what you do is you essentially take a saturated vapor or a supersaturated vapor and you provide an impetus for nucleation. Now, this can happen either homogeneously or heterogeneously. Homogeneous nucleation happens when you have a sufficiently high degree of supersaturation and the kinetics favor the formation of the nanomaterial. So, the reaction as well as condensation kinetics should be such that particles can nucleate homogeneously. Heterogeneous nucleation on the other hand has a much lower energy barrier. It is much easier to get particles to nucleate on a heterogeneous surface. So, for example, if you insert this cold finger as it is called, which is essentially a cooled surface, then particles will immediately nucleate preferentially around the circumference of this object that you have inserted. Once nucleation occurs, you can relieve the remaining supersaturation by condensation or reaction of the vapor phase molecules on the resulting particles. So, the nuclei that are formed start growing by these two mechanisms: condensation of the vapor that is still left in the gas phase onto these nucleated particles, as well as reaction between the vapor phase molecules and the resulting particles. So, this is what initiates a particle growth phase. If you recall that trimodal particle size distribution that we had sketched in one of the earlier lectures, the nucleation process has to be followed by a growth process in order for the cluster sizes to keep increasing. Now, sometimes you do not want the growth, you want the nuclei to remain as nuclei, you want the dimensions to remain essentially a few nanometers in size rather than growing to tens of hundreds of nanometers. Then what you need to do is quench the growth. So, do not allow the particle growth to happen. Now, how do you do that? You have to remove the source of supersaturation. You have to immediately shut off the flow of the vapor in order to eliminate the source, or you have to slow the kinetics of the growth phase. Now, the coagulation rate is proportional to square of number concentration. So, the more concentrated the vapor phase is, the greater will be the rate at which these nuclei coagulate. So, a simple way to reduce coagulation or growth kinetics is to reduce the concentration of the reactive vapor in the gas phase. Coagulation rate is, interestingly enough, only weakly dependent on particle size when we are doing vapor phase synthesis of nanomaterials. As temperatures increase, coagulation is replaced by coalescence or sintering. The primary difference between coagulation and coalescence is that at low temperatures where coagulation happens, you form loose agglomerates with open structures. At intermediate temperatures, you get partially sintered agglomerates which are non-spherical in form. At high temperatures where coalescence dominates, you form spherical particles. So, control of coagulation and coalescence is critical. You can control not only the size of the nanoclusters, but even the shape of the nanoclusters. So, the point is coagulation is a low temperature process and it results in the formation of flaky, porous, amorphous type of clusters. As you keep increasing the temperature, you get a more and more crystalline material, and at extremely high temperatures you get coalesced, sintered, crystalline particles. So, depending on what you are looking for, you can essentially control the temperature to achieve the structure as well as the size that you are looking for. Now, nanoparticles in the gas phase always have a tendency to agglomerate, as we have discussed extensively in previous lectures. Loosely agglomerated particles can be redispersed with some effort, but when agglomerates are sintered or partially sintered, it becomes very difficult to redisperse them. So, for example, if you have particles that are loosely adhered into clusters, you can essentially use mixing, agitation, or even sonication to break them apart into individual particles and nuclei. But at high temperatures, when they have sintered together, you cannot use any physical means to really break the cluster apart into its individual components. Now, liquid phase synthesis is a slightly different technique. The most common example of it is the sol-gel method. It is used for preparation of quantum dots, which are semiconductor nanoparticles. The method can also be used to synthesize glass, ceramic, as well as glass ceramic nanoparticles. Dispersion can be stabilized here by capping the particles with appropriate ligands. The difficulty in the sol-gel method is that it is actually a combination of bottom up and top down. You essentially make a powder of the material using a bottom up approach, but then you have to grind it down to the nano dimensions by using a top down approach, and as you do that, dispersion can become an issue. Reagglomeration can be a problem, which can be avoided by essentially preventing the particles from attaching to each other by capping them. So, here is a schematic of the sol-gel method. The sol-gel method can be aqueous or alcohol based. It involves use of molecular precursors, primarily alkoxide or metal formates are used. The idea here is to take a mixture of the constituents, liquid phase constituents, stir them until you form a gel. It should have the consistency of a gel. The gel is then dried at 100 degrees centigrade for 24 hours over a water bath and then ground to a powder, and that is where the top down process comes in. This powder is then heated gradually at 5 degrees centigrade per minute, then calcined in air at 500 degrees to 1200 degrees centigrade for 2 hours. Now, the advantage of this is that the mixing is occurring at molecular level. So, that is the bottom up approach, but then the size control is achieved by a top down approach. So, to some extent it combines the best of both worlds. You get very high purity materials using this technique, low sintering temperature. Essentially this process can be run without resorting to high temperatures, which introduces all the problems associated with sintering. The degree of homogeneity you can achieve is quite high. It is particularly suited to the production of nano-sized multi-component ceramic powders. The reason for that is twofold. Multi-component because you can take many different precursors in liquid form, mix them to form a gel and then grind them down. Ceramic is particularly advantageous because this top down approach of grinding to achieve a final size works particularly well for materials that are hard and brittle, and ceramics satisfy both requirements. They are hard as well as brittle, so it makes it very easy to grind them down to a certain size. Now, gas phase synthesis is actually very similar to what we had termed earlier as vapor phase synthesis. The difference here is you have a background gas into which you are vaporizing material, and the supersaturation here is achieved by vaporizing a material into a background gas and then providing appropriate cooling of the gas to achieve the supersaturation. These gas phase synthesis methods can be further classified based on the form in which the precursors come in. The precursor or the material that is vaporized can be in solid form, or it can be in liquid or even vapor form. The methods that use solid precursors of material which then get vaporized include inert gas condensation, pulsed laser ablation, spark discharge generation, ion sputtering, and methods that use liquid or vapor precursors or chemical vapor synthesis, spray pyrolysis, laser pyrolysis, photochemical synthesis, thermal plasma synthesis, flame spray pyrolysis, low temperature reactive synthesis, etc. We will just look at a few examples of these. This is a schematic of an inert gas condensation process, which is particularly suited for production of metal nanoparticles. Now, these metals have reasonable evaporation rates at attainable temperatures. So, as we saw in the previous slide, the first step is to take the precursor and convert it to vapor form. So, in this case the precursor is solid metal. Now, to convert it to vapor form simply by heating is not something you can do for all metals, obviously. So, only certain metals lend themselves to this method of vaporization. So, here the procedure is to heat the solid and evaporate it into a background gas, mix the vapor with a cold inert gas to reduce the temperature, and then essentially you introduce reactive gases in the cold gas stream to prepare compounds, if you like. For example, if you are trying to make a nano oxide, you can do that by introducing a stream of reactive gas into the cold gas stream. If you are only trying to make nano-sized metal, then simply heating the solid into a background gas and then cooling it is sufficient to produce a supersaturation, which can then be relieved either homogeneously or heterogeneously to produce the nucleates. You can also do controlled sintering after particle formation to prepare composite nanoparticles. Various examples are given here. So, this essentially a two-stage process where you first do a low temperature process to make nanoparticles that have essentially a loose structure, and then you do a high temperature sintering to provide a more specified composition and structure by introducing multiple precursors into the reacting mixture. Pulsed laser ablation is another way to vaporize material. So, for metals that cannot be vaporized simply by heating, you hit the metal surface with high energy laser and it vaporizes essentially a plume of material. Some of the advantages of this technique is it can be very localized. You can hit certain geometries on the surface and vaporize the material only in that area. So, it is tightly confined both spatially and temporally. What we mean by that is you can confine your vaporization to a small zone of the metal, and also you can do it for a fixed amount of time, and all you have to do is turn the laser off and that stops the vaporization process. So, you achieve both spatial control as well as time control using this process. The drawback to this method is it's because of the way it works, it can only produce small amounts of nanoparticles. It is not a bulk production process. But the advantage of course is that it can vaporize metals that cannot be easily vaporized just by heating the metal. For example, silicon, magnesium oxide, titania, these are materials that have fairly low vapor pressure and they have to be heated to extremely high temperatures in order to get them to vaporize, and for such materials this laser ablation process works very well. And there is a strong dependence of particle formation dynamics on the background gas. So, simply by changing the nature of the background gas, you can affect the kinetics with which particles are formed. You can again control the size, shape as well as the chemical composition of the nanoparticles by changing the nature of the background gas. For example, by changing from an inert gas to let us say air, you can actually produce oxidized nanoparticles. Spark discharge generation is another technique to take solid metal and vaporize it. So, here you essentially make electrodes of the particular metal to be vaporized and you charge them in the presence of an inert background gas until you reach a breakdown voltage. Above that voltage, an arc forms across these metal electrodes and vaporizes a small amount of the material, which can then be used to make nanoparticles of that material. Example is nickel. Again, the drawback is it produces very small amounts of nanoparticles, and the advantage is it is a very controlled, repeatable and reproducible process. And just like in the pulse laser ablation technique, by using a reactive background gas you can make compounds, by using oxygen you can make oxides and so on. The background gas itself can be pulsed between the electrodes as the arc is initiated, and this is called the pulsed arc molecular beam deposition system. Ion sputtering is another commonly used technology, where in this case you are essentially impacting the solid surface with high energy ions. So, this process is called sputtering. Sputtering refers to hitting the solid surface with a beam of gas ions. Again, these can be inert or reactive as the application demands. Magnetron sputtering is a name that is commonly given to equipment that is used for this process of sputtering of metal targets to produce metal vapor. It requires low pressure, approximately 1 millitorr. And one of the drawbacks to this method is that further processing of nanoparticles in aerosol form can be difficult because of particularly the low pressure environment that is demanded in ion sputtering techniques. Chemical vapor synthesis is probably the most widely used method to make nanoparticles in the bottom up approach. Here you take vapor phase precursors and you bring them into a hot wall reactor under nucleating conditions. So, essentially this is a reactor in which there is a target surface, but even the walls of the chamber are heated to high temperatures. Because of this, the entire reactor is in a condition where it promotes nucleation. So, vapor phase nucleation of particles in this case is favored over film deposition on surfaces. For those of you who are familiar with chemical vapor deposition, this is the exact opposite of that. In a CVD reactor, you try to design the reactor conditions such that the nucleation only occurs heterogeneously on the target surface on which you are trying to put down a film. In a CVC reactor, that is a chemical vapor condensation reactor that is used to synthesize nanoparticles, the reactor is designed very differently. All the walls of the chamber are also kept at elevated temperatures, so that, and the gas itself is kept under conditions such that homogeneous nucleation becomes possible. This minimizes heterogeneous nucleation on the target surface. The advantage of this technique is it is very flexible, can produce a wide range of materials. You are only limited by what vapor phase precursors you can make. So, anything that can be made into a vapor phase form and introduced into the reactor can be made to react and produce product that is in the nano size range. From the viewpoint of analyzing and characterizing such reactors, there is a huge database of precursor chemistries that has been developed by the CVD industry. Chemical vapor deposition has been used for a long time to make thin films for various applications. So, the CVD industry is very mature and it has a huge database on various chemical reactive components and the associated products. So, in chemical vapor synthesis, you can take advantage of this pre-built library of data. The precursors can be solid, liquid or gas under ambient conditions, but they must be delivered to the vapor to the reactor in vapor form. It is critical that you do not allow solid or liquid reactants to enter a CVS or CVC reactor. The reactants have to enter in vapor form, but how you convert the solid or liquid precursors to this vapor form is entirely up to you. You can use bubblers, sublimators, etc. Some examples of nano materials that are used, that are manufactured using a chemical vapor synthesis reactor are oxide coated silicon nanoparticles, tungsten nanoparticles by decomposing of a tungsten compound, Cu and CuXOY nanoparticles also from a copper compound. The next technique is spray pyrolysis. In spray pyrolysis, essentially we make very small droplets of the precursor using a nebulizer, and you inject it into an evaporative environment. This technique is also known as aerosol decomposition synthesis, and it involves a direct conversion from droplet to particle. The reaction here takes place in solution in the droplets. These very fine sprays or droplets are again highly reactive because of their small sizes. So, they react and then you evaporate the solvent that you have used to make these fine droplets, and you get the compound that you are looking for. Titanium oxide and copper nanoparticles are examples of materials that are conventionally manufactured using this spray pyrolysis technique. A related technique is laser pyrolysis or photothermal synthesis. Here the precursors are heated by absorption of laser energy, and this technique allows highly localized heating and rapid cooling. So, quenching becomes easy when you are using this technique. You do not have to allow growth to occur beyond a point where you want to stop it. Infrared laser, CO2 laser can be used, which reduces the expense of the operation. Some examples of materials that are made using this technique are silicon from silane, MOS2, silicon carbide. Pulsing the laser shortens the reaction time and allows preparation of even smaller particles. So, the laser pyrolysis method is again widely used to make small quantities of nanomaterials. We will stop this lecture at this point and we will consider more examples of bottom up synthesis in the next lecture, and then we will continue our discussion by looking at methods of top down synthesis of nanoparticles. Any questions? See you at the next lecture then.